Hello, my name is Jeremy Guevara. I am a student studying mechanical engineering and my study of interest is thermodynamics, fluid mechanics, and vibrational analysis. I hope to find a career in sustainability, such as in energy production or methods of improving renewable energy sources, to help the world adapt to climate change in a meaningful and efficient way. My hobbies include playing the bass guitar, watching movies, and biking. One quote that has stuck with me for as long as I can remember, spoken by Cornel West, is, "You've got to be a thermostat rather than a thermometer. A thermostat shapes the climate of opinion, a thermometer just reflects it."
My name is Jacob Yarmar. I'm a mechanical engineer major, hoping to get a job somewhere in the automotive industry. My favorite sports to watch right now are basketball and any kind of motor racing, especially Formula One. My dream job is to be a racing engineer for a racing team. My main hobbies right now are racing on my simulator and training my dog. One of my favorite quotes comes from the movie Talladega Nights, where the father of Ricky Bobby says, "If you're not first, you're last."
Hello, I'm Christian Puentes. I'm a mechanical engineering undergraduate here at FIU, and my primary interest is in fluids and thermodynamics, which is why I want to go into aerospace or energy production. I don't really keep a lot of quotes in my head, but I do like this quote from Sun and Steel, which goes, "The iron does not lie, it reveals the truth of one's inner strength." So I think that's pretty interesting.
Internal combustion engines have been one of the most important engineering marvels of all time, since its initial inception in 1857 by Eugenio Barsanti. In the design of an internal combustion engine, each one of its components must meet all of the design considerations unless we want to risk failure in the entire engine, which could cause a catastrophe. In this study, we are going to perform a mechanical design analysis on the fundamental building blocks of an internal combustion engine to see if this design holds up to the appropriate standards. We're going to be analyzing the maximum stress, strain, deformation, and factor safety for each of the parts while under a typical loading during the typical operation of an engine. This will help us determine where failure will occur first in our assembly and whether or not this is a valid design. Then, we will perform a transient thermal analysis to plot the temperature distribution over time to see how the assembly reacts to the high temperature of combustion. We will also perform a buckling analysis on the connecting rod. Finally, once we've determined the efficacy of our design, we will perform a design optimization analysis to synthesize all of our design considerations to find the best material for this engine.
So to preface all of our simulation settings, we made the basic assumption that the peak pressure of combustion would be 300 psi. So given the area of our piston head, which is about 12 square inches, we'll get 3,651 pounds of force for every single simulation that uses a force. The static compression study for the piston head was done by applying the force onto the top of the piston and having a fixed support at the top half of the holes where the pin would go to sort of model that instant where combustion occurs and the pin reacts on the inside of the piston head. For all of our thermal studies, we took the top of the piston head as 1811 Kelvin, and we applied some convection loads on the sides of about 50 watts to model any cooling from, engine oil. And on the inside surfaces of the piston, we have radiation there, whose emissivity coefficient is about 0.8 and has a view factor of 1. All of the ambient temperatures are 20 degrees Celsius, so 293.15 Kelvin. You'll notice that the inside of the grooves there at the piston head don't have any thermal loads on them because there would be O-rings there and they act as an insulator. For the transient heat transfer analysis simulation, we did a total time of 300 seconds and we took plots every 60 seconds. For the piston pin shear study, we have two forces of 1,825.5 pounds force, which is just the force that we got before, but divided in two because it's over two equal areas. And we have one fixed support at the bottom half because that's to model any reaction from the connecting rod.
For the connecting rod, we're going to be analyzing both the compression and bending moment cases. For the compression case, we're going to be modeling the instant combustion occurs and the piston pin acts downward on the inside of the connecting rod. The crankshaft then reacts on the upper inside of the surface of the connecting rod and is then modeled by a fixed support at that location. Then, in the bending moment case, we're going to be modeling the forces acting on the rod when it reaches its maximal angle relative to when it's perfectly in line with the piston head. In our case, this is 13 degrees. We will also be evaluating the buckling scenario in both of these cases, where we keep all the forces and friction the same with a mode shape of 1.
For the crankshaft, we did two different kinds of studies, a bending study and a torsion study. For both of the studies, we fixed the outer parts of each end, but not including the faces. For the bending study, we orientated the parts so that the load would be directed downwards towards the middle of the part. In the case of torsion, we orientated the parts so that the load is perpendicular to the distance from the rotation axis, creating torque. The optimal design study shows an optimized part that takes into account which material is best to meet the design requirement. For the crank, we limited the minimum factor of safety to only take values for when the factor of safety is greater than 2. We set up the study so that it would minimize the stress on the part as well. In this study, we decided to optimize the material that would be used to create the part. Originally, we chose 2014 aluminum alloy as the material. In the design study, we selected 3 other materials to compare with the results of the original material. The materials selected being 2024 aluminum alloy, malleable cast iron, and cast carbon steel. Based on the results of our simulations, we can see that aluminum alloy 2014 is not the best choice of material for this internal combustion engine. Not only does it yield in certain parts for the typical applied load, such as for the connecting rod where it yields, but it is generally a more expensive material by the pound at around $4.35. Our optimal design study exemplifies this even further, in which it is one of the worst materials when compared to more traditional material for engine use. Furthermore, cast carbon steel, the best choice of material according to the design study, has a lower cost per pound at around $3.44, making it a more viable option. Ultimately, our original hypothesis of aluminum alloy 2014 being the better material for this application was incorrect. While cast carbon steel seems to be the best material for this application, further testing and simulating can be done to make a more refined and informed decision on which material is best for an internal combustion engine. This simulation should be scaled up to see how the individual components of our engine react to loads in a typical 4 or 6-cylinder engine.
Thank you everybody for taking the time to watch our video and hear our opinions. We really appreciate supporters like you.